Hello everyone, welcome back to the new section of numerical methods. Under this section we have already learned about the trapezoidal rule for finding out the numerical integration, and in this lesson we are going to learn about the Simpson's rule, another advanced approach to find out the numerical integration. Remember that Simpson's rule is another closed method, and it's also one of the Newton course formulas that we are going to learn in this course. And trapezoidal rule, it was also a closed method and a Newton course formula. But Simpson's rules, these are more advanced than the trapezoidal rules. So let's find out the basics of Simpson's rules. If you remember, in trapezoidal rule, we segmented the portion under the curve within the boundary with a separate trapezoids. So can you just remember why those trapezoids emerged? Because we connected each of the data points within the boundary with a straight line. As a result, the upper portion looked like a straight line connected. As a result, each of the segments appeared like a trapezoid, and that's why we call those method as trapezoidal formula. Okay, so that was the basic of trapezoidal rules. But in Simpson's rule, we connect each of the data points within the boundary with a higher order polynomial. In trapezoids, we connected these boundaries with a straight line, but in Simpson's rule, we connect these data points with a higher order polynomial. And that's the difference between Simpson's rule and trapezoidal rule. Since we are connecting these points with a parabola or cubic polynomial, whatever, or higher order polynomials, we are actually capturing the more features of the data points. As a result, they are approximating the area under the curve more precisely. Okay, so if you just think about, this is a segment under a curve, and we want to fit a parabola with these two data points. Okay, but to fit a parabola, we have to find out another data point within this boundary. So let's say under this segment, in this segment we have another middle data point here, and we can easily fit a parabola in this segment. Okay, so that's the basic, we can easily fit a parabola. So let's say we have two other data points under this segment. So what will happen if we have two other data points? In total there we have 4 data points. So we can easily approximate the curve here with 4 data points with a cubic polynomial fitting. Okay, we can easily calculate other data points and go for higher order polynomials. So that's the basics of Simpson's rule. We just connect each of the segment with a polynomial, which can be a quadratic equation or a cubic equation or a higher order equations. Okay, so let's first look at Simpson's 1/3 rule. Okay, how this formula came into effect. So this is the main equation of integration. F of x is the function. Let's say I want to use a second order in a polynomial to connect the dot points under a segment. Okay, so I will need 3 data points. Since already I have the 2 boundary points in a segment, so I need another data point within this segment. So that will make me use a second order polynomial to connect the boundary points. Okay, so that's why we have just changed the function value. The notation here is f2 of x. Okay, so if you just say that these a and b values, these are denoted as x0 and x2, so we can easily form a second order Lagrange polynomial with these 3 values, with f of x0, f of x2, and a function value, a third function value within the boundary. So we can easily apply the second order Lagrange polynomial. So if you do not know the second order Lagrange polynomial, this was covered in the last segment whenever we were discussing interpolation. So second order Lagrange polynomial is a very basic function which is used in interpolation or integration, something like this. So the second order polynomial can be easily represented something like this. This is a second order Lagrange polynomial equation. Okay, so you already know how this equation was formed, how there is a pattern within this equation. So please go through the details of Lagrange polynomial interpolation in the last segment. So whenever we just replace this f2 of x, this function, with a Lagrange polynomial, the whole function looks like this. Okay, so after some algebraic manipulation and integration, the function simplifies to this form. In this form, h is denoted as the difference between the segments. That means h equal to b minus a divided by 2. In trapezoidal rule, we denoted this as the width of the each segment. In this case, this is also the width. This is the width of average width of a segment. Okay, this is the average width. So in Simpson's 1/3 rule, we are just calling this Simpson's 1/3 rule because there is a multiplicative factor of 1 by 3. This is the that's why this is called Simpson's 1/3 rule. The level 1 by 3 denotes its name. So the alternative form of Simpson's 1/3 rule can be achieved if we just substitute the value of h by b minus a divided by 2. And then the formula simplifies to this form. This b minus a, this is the width, and the average height, this is denoted by this. This is the average height of each segment. F of x0, f of x2, these are the function values at the boundaries of this segment. And for f of x1, f of x1 is the function value at an intermediate point within this boundary or the segment. Okay, this is the average height. So that's the modified Simpson's 1/3 rule that we can directly apply to tabulated data or functions or equations. So let's say we want to segment the portion of the curve under the curve with more segments. Okay, let's say we have now n segments. Then the average width of each segment can be easily calculated by this, h equal to b minus a divided by n. So this is the average width of each segment. So the total integral can be now represented something like this. So each segment can be easily represented a separate segment with separate Simpson's 1/3 rule. So each of these segment has a separate 1/3 rule. So if we just simply input the Simpson's 1/3 rule for each of these segments, the equation looks like this. So this is the Simpson's 1/3 rule for the first segment, this is for the second segment, and this is for the third segment. Okay, so if we just simplify this whole equation, we will get an equation something like this. This is the total or complete Simpson's 1/3 rule for n segments. In the first case, we just formulated for 2 segments, but right now we have n segments, and this is the general formula of Simpson's 1/3 rule. So this is the width, and this is the average height of all of the segments. So here we have the f of x0, the function value at the first data point, and f of xn, the function value at the last data points. This is the summation of function values of segments with odd sequences, where I equal to 1, 3, 5. That means this is the summation of odd segments, and this one is the summation over the even segments, even number of segments. So segments with even sequences. So second segment, fourth segment, sixth segment. So this is how this works. Okay, so in the odd segments we have a multiplicative factor of 4, but in the even segments we have a multiplicative factor of 2. So please note these differences. So that's the general formula of Simpson's 1/3 rule. So if you just go through the figure, you see in trapezoidal rule we just connected these data points with a straight line, but right now we are just connecting these data points with a second order polynomial. So that's a better approximation of the function within this segment. So each of these segments, within each of these segments, we are just connecting these dot points with a second order polynomial. Okay, so that's a better approximation than the trapezoidal rule. Okay, so let's look at an example. We have a function f of x is this. So we have already seen this function in trapezoidal lesson, and this was the same example that we covered in that lesson. So we have to use the Simpson's 1/3 rule, but with a number of segments equal to 4. Okay, we have the limits, lower limit is 0 and the upper limit is 0.8, and for your reference the exact integral value is given here, 1.640533. So how we are going to apply? We have 4 segments, so we can easily calculate the width of each segment, which is h equal to the upper limit minus the lower limit divided by number of segments equal to 0.2. And we just calculate the function values at each of the boundary points. That means at x equal to 0, at x equal to 0.2, x equal to 0.4, 6 and 0.8. so at each of these boundary points we just calculate the function values. Okay, now we have all the elements to apply the Simpson's 1/3 rule. These are the function values. So applying to the Simpson's 1/3 rule, we can easily get the integration value. Okay, look at this. These are the function values at odd number of segments, and this is the function value at even number of segment. So the first segment we have a height of the first function value at the boundary, lower boundary, which is 0.2, and this is the function value at the last boundary, which is 0.232. Okay, so we can, this is the value of width b minus a, and this is the multiplicative factor. So we have the integration value, which is 1.623467, and if we compare with the true value, we will have a percentage error of 1.04% only. Okay, so this is the percentage which is very low, and with more segments we can easily go to the exact value, go toward the exact value with smaller percentage of error. So that was the Simpson's 1/3 rule. So in a similar fashion, we can easily calculate the integration with Simpson's 3/8 rule. So in Simpson's 1/3 rule, we connected each of the dot points with data points with a second order polynomial, but in Simpson's 3/8 rule, we use a third order polynomial. That means we have to use the third order Lagrange polynomial into these functions. So that's the same procedure, but in Simpson's 1/3 rule we use the second order Lagrange polynomial, but right now we are going to use a third order Lagrange polynomial. So if you just simply put the values of put the values of Lagrange polynomial, third order Lagrange polynomial, and simplify the equation, you will get this form of equation. So this is Simpson's 3/8 rule. Why? Because we have a multiplicative factor of 3/8. That's why it is called Simpson's 3/8 rule. Okay, so if you just simply put in the values of h, which is b minus a divided by 3. Now why we are dividing with the 3? Because we are just fitting a third order polynomial, and to fit a third order polynomial we need 4 data points within a segment, and with 4 data points we will have 3 inner subsections, and that's why we are just using the factor here 3. So h is the average width of each segment. Okay, so and that's why it is called Simpson's 3/8 rule. We have the multiplicative factor 3/8, and we are dividing with the value 3 to calculate the value of h. Okay, so in Simpson's 1/3 rule this was 2 because we were using a second order polynomial, but right now we are using third order polynomial, and we need 4 data points, and that's why we need 3 intermediate segments, and that's why we are dividing it with a value of 3. So Simpson's 3/8 rule can be easily expressed in this notation. We have just substituted the value of h here. As a result, this is the general, this is the notation of a Simpson's 3/8 rule with just one segment. Okay, we can easily go for the higher number of segments. Let's say we have n segments. We can easily form the basic equation, the general equation of Simpson's 3/8 rule. So remember, Simpson's 3/8 rule is good for whenever we have odd number of segments, but Simpson's 1/8 rule, it should be 1/3 rule. Simpson's 1/3 rule has utility whenever we have even number of segments. So what we can do, we can just combinedly use both of these formulas in a same problem. For example, if we have 5 segments, and we can easily use the Simpson's 1/3 rule in the first 2 segments and Simpson's 3/8 rule in the last 3 segments. Okay, this should be 1/3 rule. I'm sorry, this is a mistake. It should be 1/3 rule. So that was the difference between Simpson's 1/3 rule and 3/8 rule. And so in this table, we are just summarizing the formulas of trapezoidal rule, the Simpson's 1/3 rule, and Simpson's 3/8 rule. So these are the equations that are being used for each segment. Okay, we can apply these equations at each of these segments. We have another formula which is Boole's rule. Simpson's 1/3 rule uses the second order polynomial. Simpson's 3/8 rule uses the third order polynomial, and the Boole's rule, it goes for higher order polynomial. So these are all of them are actually the same procedure. We are just connecting the data points with different order of polynomials. In trapezoidal, it was first order polynomial, that means it was a straight line. In Simpson's 1/3 rule, it was a second order polynomial, that means it was a parabola. In Simpson's 3/8 rule, it was third order polynomial, that's why it is a cubic polynomial. And in Boole's rule, we have higher order polynomial, and it was a fourth order polynomial actually. So that was the end of this section, end of this lesson actually. We have covered the Simpson's 1/3 rule and Simpson's 3/8 rules. So that we have known the basic differences between these two methods, and we have seen that Simpson's rules are actually more precise than the trapezoidal rules. And we have seen that these trapezoidal rules and Simpson's rule, those are of actually under the same category. We are just connecting the data points with different orders of polynomials. Okay, so I have attached the MATLAB code for Simpson's 1/3 and 3/8 rules. Please go through the details of the MATLAB code so that you can understand how these methods are being applied practically in MATLAB codes or other codes. In the next lesson, we are going to learn about the integration result whenever we have unequal space data. In these examples that we have covered in this lesson and in the previous lesson, we have seen that these data points that we are given, those are of equally spaced data. But what will happen if we have unequally spaced data? So that is the main concern in our next lesson. So till then, thank you so much.